Kia ora koutou, no mai, haere mai. Welcome to lesson 19 for introductory physics. This lesson is the first one of the second half. And as you'll hopefully have read on stream, the second half is going to be a little bit different from the first half. During the first half, we did divide it into different sections, but they all amounted to the subject of mechanics. So they were all looking at the motion and interaction of different objects through forces being applied and through collisions and energy conservation and all of that. In this second half, what we're going to do is we're going to jump around between a few different topics in physics. And the first one we're going to look at is the substances that make up matter. So solids, liquids, and gases, and the fact that they're made of atoms. So we're going to start by looking at matter being made of atoms. As usual, we'll jump over and we'll read through our lecture slides. Matter is atoms. The goals today are to understand Brownian motion. You're not going to need to be able to do any analysis on it or to be able to describe it mathematically, just be able to describe it qualitatively. Remember that distinction between quantitative and qualitative? Throughout this half of the course, you'll find that there's actually quite a lot of qualitative discussion. We did a lot of quantitative work in the first half of the course because we had the equations and we had the maths and we were able to do that to analyze those different scenarios. In this half of the course, we'll still do that. We'll still have quantitative analysis here and there, but we'll also intersperse it with qualitative discussions where we just talk about the topics a little bit and describe things and think about how things work without getting into the mathematics of it. So to start with, we're going to do that. We're going to talk about Brownian motion qualitatively and use it as justification for the existence of atoms. We're then going to move on to describing the general characteristics of atoms, but we're not going to go too far into atoms. We're actually going to come back to them in the next section, possibly the next one, I forget the exact order, and we're going to look at what they're made of. But for now, we're just going to talk about atoms more as a whole. We're then going to talk about the different phases of matter, and we're going to explain the difference in atomic structure of each of those phases. So solids, liquids, and gases are the ones you will have already heard of. And then we're going to briefly return to density that we already met when we were talking about objects and talking about their volume and how much mass they had per unit volume, and just think about how density and atomic structure are related to each other as well. First though, before we do any of that, I want you to just take a breath. Take a deep breath in, right, and then release it. Now we're going to think about that breath that you just took. So you've hopefully just done that. For the average person, that breath was around about half a litre. That's an average lung capacity, it's about half a litre. At its normal air pressure, so the air pressure that we just live in, atmospheric pressure, half a litre of air consists of 1.25 times 10 to the 22 atoms. So I've written that down. That's how many atoms you just breathed in that single breath. 12.5 sextillion atoms, if you want to use the numerical term sextillion in there. So that is a lot of atoms that you just breathed in. The ones you exhaled, which would have been just as many, but they weren't necessarily the same ones as the ones you inhaled, because some of the ones you inhaled, you absorbed into your body and is being put to use. And of course, that's the purpose of breathing. You're breathing some in, you use some of them, you exhale slightly different ones. But that number is pretty consistent, around about half a litre of air for a full breath in, and that means about 12.5 sextillion atoms. And everyone around the world is constantly doing this for their whole lives. That many atoms with every single breath. The total number of humans that have ever lived. So right now on Earth, there's around about 7 billion, a bit over 7 billion. The total that have ever lived on Earth is around about 110 billion. So 110 billion humans ever versus 12.5 sextillion atoms in a single breath. That's how many atoms there are. That's how small they are to fit that many into a single breath. After a few minutes, those air particles you exhaled will disperse throughout the room you are in. This is assuming you're inside in some kind of room. If you're outside, obviously they'll disperse throughout the entire environment. If there is a breeze, so if you've got a window or a door open and there's a bit of airflow, then they will disperse a bit more quickly. If you're shut up in a room with it that's got fairly still air, then they'll take a bit longer to disperse, but they will still disperse. They'll spread out throughout the whole room. So there were 12.5 sextillion just in that lungful. Imagine how many there are in the whole room, and the ones that you breathed out are going to spread out and mingle right throughout all of those particles in the air. After a couple of days, those particles will be outside. They'll be spreading through the environment. They will go across thousands of kilometers. Air particles move very quickly. We don't feel them because they're so tiny, but they are moving. I shouldn't say we don't feel them. We definitely do feel them. We'll get onto that. But they move very small, very quickly, but they're very small. So there's not a lot of impact that we notice. I'm getting ahead of myself there. Anyway, they move very quickly. They move thousands of kilometers across a couple of days. After a couple of months, depending on where you are, where the wind currents carry them, and what the weather is like, those atoms that you breathed out, those 12.5 sextillion atoms that you breathed out, will spread out across the majority of the southern hemisphere. Assuming you're in New Zealand or Australia, then it will be mostly around the southern hemisphere. That's just the way the air flows, the air currents sort of work, the weather patterns. If you're in the northern hemisphere, similar sort of thing, they'll spread out throughout parts of the northern hemisphere. And that's only going to take a couple of months to do that. After a couple of years, then those particles that you breathed out will be pretty well spread across the entire globe. The entire planet Earth, the entire atmosphere of Earth will have those particles that you breathed out spread out throughout it. They'll be everywhere. In the atmosphere, there are approximately 4 times 10 to the 21 litres of air in the whole atmosphere. Right, so that's a lot of air. That's if you stored it all at standard atmospheric pressure and temperature. And you will recall when we mentioned atmospheric pressure, it actually decreases as you go up. So it would be more volume than that because some of it is less dense. But at the density of our standard air pressure, then it would be around about 4 times 10 to the 21 litres of air. If each breath is half a litre, that means there are about 8 times 10 to the 21 lungfuls in the atmosphere. That means for every lungful of air in the atmosphere, there's an average of 1.5 of the particles you just exhaled in that breath. So every breath of air around the globe would have an average of 1.5 of the particles that you just breathed out. And the same for me and the same for every other student that is taking this course. So they spread out and everyone around the world is then going to be able to breathe them in. So with every breath you take, everyone that is alive that has ever lived, you are likely to be breathing in 1 or 2 of the particles that they have exhaled. Remember that was just one breath we're talking about, and we're talking about 110 billion people over the entire history of the human race. Every breath you take is going to contain particles from many, many of those people. The probability itself is extremely difficult to calculate. There are very large numbers and the mathematics don't really hold up. But given everyone breathes for their whole life, and we're breathing that many atoms over and over again, it's a very high probability that you have a very large percentage of the population's previously owned particles in your breath. Around 20,000 breaths a day is the average, and a lot of them will recycle. If you're in the same room, then when you breathe in, a lot of those 12.5 sextillion atoms are going to be the same as the ones that you just breathed out, and so on. But overall, there will be a lot of breaths every day, every year, and therefore a lot of particles that you have at some point inhaled and exhaled spread throughout the globe. So we're all existing in this sea of previously owned atoms. So you're likely to be breathing in particles that have been inhaled and exhaled by every human to have ever existed. Of course, there is the exception that there are children that are young, they haven't had time to have particles that have been breathed in and out and spread throughout the globe yet if they're less than a couple of years old. But everyone else, from Mahatma Gandhi to Einstein to Adolf Hitler, we all share the same air. We're all breathing in particles that they have breathed in and breathed out. Now, there's no real purpose to this discussion. There was no real reason for me to bring all of that up. I just wanted to try and drive home the idea that these atoms are really tiny and that they're everywhere. Right? They are everywhere, they're tiny, we're always constantly interacting with them through our breathing and just living, but they are very, very small. So that's what we're going to look at now. Proof of atoms. They're so small that people didn't really think they existed. Even the scientists didn't think that atoms were real. They thought they were just a great way to talk about material without actually being a real thing. And of course, it's not just air that's made up of atoms, it's everything that's made up of atoms. Right? You, your body, everything, all your stuff, the entire Earth, the entire atmosphere, the sun, everything is made up of atoms. So if it's all made up of atoms, but scientists didn't really think it exists, then what did they think? Well, they thought that atoms were just too small to really be individual things, and that everything was just sort of like a I don't really know how to describe it, just a lump of stuff. Right? So just a lump of stuff instead of being made up of little tiny blocks. So you can think of atoms like little Lego blocks and you build everything out of them. They didn't think that, they just thought it was one big lump of plastic rather than made up of all these tiny blocks. And that's because atoms are so small. If everything is made up of them, but they are really small, then we have to have lots of them. Right? So Robert Brown, he was a botanist. In 1827, he noticed pollen grains. So this is a photo, it's not his original ones, but it is, I should say, a GIF of pollen grains moving on the surface of water. And this is exactly what Robert Brown noticed. He noticed that pollen grains were moving, jiggling around when he sat them on a layer of water. And he thought perhaps the pollen was alive. That was his first thought, because he was a botanist and he was studying plants, and we know plants are alive. He thought maybe the pollen grains themselves were actually alive at this point in their life cycle. And so he investigated and he put coal dust onto water as well. So he put coal dust on and he saw that that too jiggled. This GIF, by the way, is not actually coal dust, it's little microplastic particles, microbeads floating on water. But same thing. He thought that coal dust cannot be alive. It makes no sense for coal dust to be alive. So that means that this jiggling that he saw wasn't evidence of life, it was evidence of something else. But he was a botanist. He had decided this didn't mean pollen was alive, so he stopped caring about it. He wrote down what he found out and he just left it. He stopped investigating, went back to his study of botany. It wasn't until Albert Einstein came along and he noticed this particle jiggling that Robert Brown had studied, which had since been called Brownian motion. And Albert Einstein realized that this was evidence that everything is made of atoms and that atoms are in fact real. They're not just a useful thought experiment tool to describe matter, they are actually a real thing. And his theory was that the jiggling was the result of the bombardment of the pollen particle by millions of tiny little water molecules. So you've got a really big pollen particle compared to these water molecules, and one water molecule hitting it wouldn't do anything. But if millions of them are hitting it, then it's going to move back and forth. Right? Well, it's going to move a little bit in the way that they hit it, and then millions hit it the other way and it jiggles back. And of course, it's being hit by millions on all sides at all times by the water. But if you get a few more on one side for one instant, then it'll jiggle that way, and a few more the other way, it'll jiggle back. And so Einstein realized this. It became his hypothesis. He tested it, and it became a theory. And everyone accepts that Brownian motion is in fact evidence for atoms being real. So as I was just saying, I've attempted to draw a diagram that hopefully explains it. If you had a single particle hit a large one, then nothing's going to happen. But if you get a whole bunch hitting it, then it will move slightly, and that is the visible jiggling that we see. So we can't see molecules or atoms with our naked eye, but we can see the effect they have on things like pollen particles or microbeads. Because the water particles are hitting it in random directions from all sides, right, that's why we get the jiggling. So we don't just get this constant movement, because the water's not all moving in one direction. The water is moving, the water molecules, I should say. The water might seem still, but the water molecules are actually constantly moving around within it. And that causes just random direction, which we call jiggling, right? We look at it and we go, oh, that's jiggling around. It's just shaking, it's vibrating. So that's what the random directions are. It's just the result of the water particles just randomly moving and bouncing into that pollen grain in different directions. And so that gives us our jittery motion. So there's that same GIF again, just for you to look at it for a moment, right? So those are real pollen grains sitting on real water being bounced around purely because they are being hit by millions of water particles. We're going to look a bit more into characteristic of atoms. I've said week 9 in that slide. This is from semester 2. Apologies for that. It's just in a different lesson. We will come back and we'll look a bit more into atoms and the properties of them. For now, all we really care about is the idea that atoms are very, very small. Remember, there are 12.5 sextillion of them in your one breathful. They make up almost everything. I say almost because there are a few exceptions. That means there must be many, many atoms. There must be heaps of them if they make up everything, but they're really tiny. We've already hinted as well at a couple more, and that is that atoms are always moving. They're vibrating or flowing or flying around, and we'll talk more about that when we come to temperature next week as well. I should say next section, not next week. Scientific notation is going to be a necessity. You may have found that you could get away without using it too much during the first half of the course, during the mechanics stuff. And so if you did get away without using it too much, that's fine, but you will need to use it now. There is literally no way for you to reliably write down the mass of a single atom without using scientific notation. Hydrogen has the smallest mass per atom, so one single atom of hydrogen has a mass of 1.67 times 10 to the negative 27 kilograms. And so I've written that out in normal notation and not scientific notation there. 0.000000, I'm not even going to read it out, all the way down to that 167 kgs. You can't work with that without using scientific notation, right? It's too easy to make mistakes. It's too easy to get things wrong. So do not try. Learn scientific notation. If you have avoided it so far, you will need it. So everything's made up of atoms. How does that work? There are different types of stuff. Right? We know there are different types of stuff. You've got a computer screen in front of you, which is made of one type of stuff. You're sitting on a chair made of another type and a desk made of another type. So there are different types of stuff. We know that, but we've said everything's made of atoms. So why are there different types of stuff if we're all made of the same little building blocks? And there are two reasons for that. One is that atoms come in different types: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, so on, all the way through to the really heavy ones that we have to make in a lab. So there are different types of atoms, and obviously if you build stuff out of a different type of building block, you're going to get a different property of material. You're going to get different things being made. But also the atoms that you do use of different types can connect to each other in different ways. So they can form solids or liquids or gases or other phases as well. We're going to discuss that second one right now. We're going to talk about building things differently out of atoms. So I'll just mention quickly on that first point, the different types of atom. Hydrogen, helium, oxygen, etc. They are all different types of atoms, which we call elements. So every different type of atom is an element. So hydrogen is an element, helium is an element, and so on. As we'll see in lesson 25, these elements are all made of the same parts. So protons and neutrons are the bits that make up these elements, these atoms, but they differ in how many of them there are in the atom. So the different elements all have a different mass per atom because they have different numbers of the things that the atoms are made of. Right? So the atoms themselves are all made of the same stuff, different protons and neutrons, but they're made of different numbers of them, which give us different masses. So the different elements do have different mass per atom, but we'll come back to that, as I said, in lesson 25. So the different phases of matter, or the different states, are solid, liquid, and gas. These are the ones you're familiar with. Solids maintain shape and volume. If you have a solid block, whether it's a block of wood or marble or steel, whatever it is, you've got a solid block, it's going to keep that shape and that volume. Unless you really apply a lot of force and deliberately deform it, that block will keep that shape and that volume. A liquid keeps the same volume, but it takes the shape of whatever container you put it in. So if you've got a litre of water and you put it in a bucket, or you put it in a vase, or you put it in a big glass, it will take the shape of whatever you put it in, but it will always maintain that volume. It will always be 1 litre of water. It is very, very difficult to compress a liquid. Almost all liquids are practically incompressible. It means that they always keep the same volume, except for temperature changes, which we will talk about again, as I said, when we move on to the temperature thermodynamics section. Gas, though, keeps neither of them. It doesn't keep its shape or its volume. It will take the shape and the volume of whatever container you put it in. If you take a litre of air at standard air pressure, atmospheric pressure, you take a litre of air and you pump it into a balloon, that balloon is stretchy, it'll squish it and it'll make it less volume. Right? It'll take the shape of the balloon and it'll become smaller in volume because the balloon is squashing it. You could also pump that 1 litre into a tiny little cube. If you've got a hollow cube and you pumped 1 litre of air in, you get up to a really high pressure. Remember, pressure is force over area. You've got this gas that will be pushing against the wall, so that's a force applied to the inside area of that box. It will be a pressure. We're going to talk about that again soon. So you can change the pressure and stuff, but you will take the shape and the volume of whatever container you try and force that gas into. So that's the essential difference between solids, liquids, and gas. Solids keep shape and volume. Liquids keep volume but change shape to whatever container you put it in, and gases will change shape and volume to match the container you put it into. Another common state of matter is plasma. You may not have heard of it. You may have heard of it just in the reference to television screens, plasma screens. Plasma is another state of matter, and technically it's a gas with its electrons that we haven't met yet and we haven't discussed yet, but its electrons have been freed from its atoms, so that there are both whole atoms minus their electron, or some of their electrons, and single loose electrons all floating around in a big gas, and that gas is called a plasma. So it's kind of like a gas, and I say gas to help you visualize what it is, but it is technically a different state because those free electrons, as I said, we haven't met them, we'll come back to this, those free electrons allow the gas to have different properties than a standard gas when we talk about just regular gases. Again, we're going to, in lesson 25, we're going to look at what makes up atoms, and this idea of plasma will make a little bit more sense. We're not going to discuss any of the other ones at all beyond plasma, but there are many other states. Solid, liquid, and gas and plasma are by far the most common, but the other states do exist, and here are some of them. Supercritical fluid, degenerate matter, Bose-Einstein condensate, fermionic condensate, superfluid, supersolid, quantum spin liquid, string net liquid, quark gluon plasma, time crystals, which aren't as exciting as they sound, I'm afraid, and Rydberg polaron. So these are different types of states, and they don't naturally occur on Earth. They're usually man-made, but they do exist as a state that matter can take. As I said, we're not going to go into them. Feel free to Google them and read up a bit if you are interested. So a solid is rigid. It maintains its shape as well as its volume. That's because every atom in a solid is bonded to all its neighbors. It can't move because it's attached to the atoms next to it. Now, if you have a stack of Lego pieces and each one is connected to all its neighbors, then you can't move that one piece because all its neighbors are attached and it would move as well. So that's what's going on with solids. Every atom is connected by what we call bonds to its neighbors. Thus, it is bonded in place. It can't move unless you just deform the whole solid. So it's held in place by those bonds. Atoms are stuck in place. The solids become rigid, and that's what a solid is. If you have a whole heap of these atoms and you want to make a solid, then you really have just two options for how you can do that. You can either organize the atoms and lay them out in a nice even grid, whether it's a cubic grid or a hexagonal grid or some other kind of shape. You could lay them out organizedly, or you could just randomly shove them together in a big pile. And that is the difference between crystalline and amorphous solids. We're not going to go into a huge amount of detail on these, crystalline versus amorphous, just being aware that there are differences. So even if you have two objects made of the same stuff, they can behave differently if they have different solid atomic structure. So crystalline solids are packed neatly into their solid form. So all the atoms are organized in some kind of nice grid, whether it's hexagonal or cubic, as you can see here. Crystal simply means array. Crystal is a regular array. So sometimes we refer to a crystalline solid as a crystalline lattice. And as I said, there are different shapes and patterns that can be made. We're not going to look at them though. We're just being aware that you can make atoms up into nice organized structures. The other form, as I said, you just randomly shove everything together and they just sort of bond to whatever's nearby. That's called an amorphous solid. And that includes glass, rubber, plastics, and many other materials. As I said, sometimes the exact same atoms, the exact same types of atoms, the same elements can form different solids, some of them being amorphous and some being crystalline, depending on the conditions they are under when they form. For example, silicon dioxide, SiO2 is its chemical symbol. Silicon dioxide, it can form quartz crystals, which are very nice crystalline, regular solids, or it can form a type of glass, which is amorphous. It's just all the atoms shoved randomly together. So the exact same elements, one silicon and two oxygens for every silicon, made into a big solid lump, could be either crystalline or amorphous. So it can take both forms. Sometimes a solid will form crystals, but it'll form multiple smaller crystals that are all slightly out of alignment with each other rather than one nice big regular crystal. and that is just called polycrystalline, poly meaning many. So it's basically saying many crystals. Here's a solid, it's either a whole big crystal, crystalline, or it's made up of a whole bunch of smaller crystal segments all stuck together, and that's polycrystalline. So polycrystalline, sometimes people refer to it as a different form of solid, but really it's just crystalline solids, but with these irregularities through it. Pretty much all metals, I shouldn't say pretty much all, many metals are polycrystals. They are polycrystalline. The photo there is a real photo, but it has had the borders between the different crystal sections of the metal enhanced using acid etching, which basically just eats away at a few of the atoms, separates them from the block of metal along those borders between the different lumps of crystal that are all bonded together. And you can notice the scale there is 30 micrometers, that mu, 30 micrometers. As we said, liquids take the form, the shape of whatever their vessel is, whatever you put them into, and that's because each atom is not bonded to their specific neighbours. They are attracted to the other liquid particles, they are bonded to the other particles, but they don't care which one it is. It doesn't care if it's sitting next to that specific atom or if it's sitting next to that one. It doesn't care, so it can move easily, right? So they can all move around, but they are still attracted to all the other particles, so they do still keep that same volume because they are attracted to each other. So they're free to move around within the liquid, they are free to flow, right? That's what we call that movement of atoms within the liquid, is a flow. And that's referring back to Brownian motion, that's what we saw when we talked about Brownian motion. The water molecules, they stayed in the water, but they all moved around, and because they were all moving around, that's when they collided with that pollen grain and caused it to move. The gas state, still made of atoms and molecules, but they are not held together in any way. Gaseous atoms are free to fly around anywhere in their container. They can bounce off other gaseous atoms, they can bounce off other molecules, and they do, they're just constantly doing that, and that's what happens in the gaseous state. So the air in your room is full of air particles, which are going to be nitrogen and oxygen molecules for a lot of it, but also a bunch of other stuff. And they're all flying around because they're a gas. So they expand to fill up your room. In fact, they expand to fill up the entire atmosphere of Earth. And they just fly around and bounce off each other and bounce off everything else. So they're not held together in any way. They're completely independent, but they just happen to collide into each other and into other stuff as they're traveling around. You may have heard the term liquid and fluid. So what is a fluid? Fluid is anything that can flow, but because liquids and gases can both flow, they are actually both fluids. So a liquid means specifically the state of matter that we call liquid. A gas is just a state of matter that we call gas, but a fluid can be either a liquid or a gas because they can both flow. The reason we have this term fluid that encompasses both of them is because there is a whole study of fluid dynamics that covers both liquids and gases, and there are plenty of phenomena that you can experience with both liquids and gases, both displaying the same results and adhering to the same equations and laws. For a given volume, the number of atoms that are in a certain amount of space is going to depend on a couple of different things. It's going to depend on what type of bonding occurs. So remember, the bonding is what holds one atom next to its neighbor. So what type of bond will determine how far apart those two atoms are. And it also depends on what type of elements are present. So what types were those atoms that made up this material. So if the elements form a organized regular structure, then you might fit a certain amount into a given volume. If you did an amorphous structure, or a liquid or a gas, you might be able to pack a different amount of atoms into that given volume. So the density, how much mass is in a given volume, is going to depend on all of that. What the atoms are, or what the elements are, and how you pack them in. Do you pack them in a crystalline structure, an amorphous structure, or is it a liquid, or is it a gas? So all of those will affect the density. As I said, we've already met density. We met it back in lesson 12, I believe it was, and it is just the mass over the volume, so M over V. Different types of atoms have different mass per atom, known as atomic mass. So density was the mass per unit volume, but now we're talking about the mass just for one single atom. So one single atom of one element will have a specific mass. Every single atom of that element will have the exact same mass. It doesn't matter which hydrogen atom in the entire universe you get, it will have the same mass as every other hydrogen atom in the universe, and the same for every other type of element. All their atoms have the exact same mass, with the exception of electrons being able to be added and removed. But the atom itself, if it had just neutral right number of electrons, would have the exact same mass. So you may think that the more mass of the atom, those bigger atoms, bigger elements that have a lot more mass per atom than hydrogen, you may think that those bigger ones would have more density, higher density, because you can, if you pack a certain number in and each one of them has more mass per atom, then you must have more mass overall. But remember that it depends on the spacing and the structure. Are you doing crystalline or amorphous? Are you doing a liquid or gas? It depends on that structure of how you pack those atoms in, as well as how heavy each individual atom is. It turns out that solid iridium is actually the densest material on Earth, but the mass of a single iridium atom is actually a lot less, I shouldn't say a lot, it's less than the mass of gold and platinum atoms. So the atoms themselves, per atom, iridium has less mass than gold or platinum, but gold and platinum are actually packed with a bit more space between each atom. And so they end up with a less density overall by the time we get to a solid block of gold or platinum. So that's everything for this lesson. We've talked about the existence of atoms, about how small they are, how scientists decided, okay, they are actually real. That was thanks to Brownian motion and Albert Einstein. We talked about the different states of matter. We talked about how you can pack the matter in, and we talked about the density of material and how that's affected by which elements are being used. So we will continue with this idea of solids being made of atoms in the next lesson, and then the one after that we'll be talking a bit more about liquids and gases being made of atoms.